All right, so this video is going to be over how we can use series to help us do other things in calculus. So the first example is how we can do composites and then figure out the Maclaurin series for that function. So our cosine overall Maclaurin series is 1 and then minus 1/2 x squared, and then plus 1 over 4 factorial x to the 4th. And this goes on and on and on. And we end up getting, all right, -1 to the n, and then x to the 2n over 2n factorial, right? Okay, so let's see what happens if I plug in then the square root. So if I want to take the cosine of the square root of x, well, I don't have an x here. Then I have 1/2 and then the square root of x squared plus 1 over 4 factorial, the square root of x to the 4th. And that ends up being alternating series still there. But what happens when I take the square root and then square it? I get x, right? And then the square root to the 4th is x squared. And then the square root x to the 6th is x cubed. So I actually am just going to have x to the n, but then I keep 2n factorial on the bottom. All right, let's look at what happens with sine. So if we expand polynomial here for sine, it ends up starting with x and then minus 1 over 3 factorial x cubed, 1 over 5 factorial x to the 5th, and our sine summation is -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, so that we have our odds, right? All right, so let's look at what happens when I plug in x squared. So the sine of x squared would then be x squared minus 1 over 3 factorial x squared to the 3rd, so x to the 6th, plus 1 over 5 factorial x to the 5th, squared to the 5th, so x to the 10th. So I'm going to plug in, you can think about this also as plugging in x squared here, right? So x squared to the 2x plus 1 over 2n plus 1 factorial. And then what would that be? That would end up being x to the 4n plus 2 . And let's see, when I plug in 0, I get x squared. When I plug in 1, I get x to the 6th. When I plug in 2, I get x to the 10th. Yep, that is our pattern there. All right, how can we use this then to help us with integration? So if I were to ask you to find this integral, you can't do that without u sub, right? Like you need something else in here. But let's be very strategic of what I can do with series to make this happen. So I know that e to the x is 1 plus 1 over x. Oh, I lied. X to the n. So x over 1, x squared over 2 factorial, x cubed over 3 factorial, and I end up getting the integral from 0 to infinity of x to the n over n factorial. Okay, so then what is e to the negative x squared? Well, 1 plus negative x squared over 1 plus, when I plug in negative x squared, I'm going to get a positive x to the 4th over 2 factorial. When I plug in a negative x I'm going to get negative x cubed over 3 factorial. So that gives me negative x squared to the n over n factorial. Or another way to write that is negative x to the 2n over n factorial. Well, let's integrate each and every one of those pieces. So that's going to be x minus 1/3 x cubed plus, let's see, 1 over 5 times 2 factorial x to the 5th minus 1 over 7 times 3 factorial x to the 7th. And then let's go ahead and figure out what that pattern is. So it looks like now I need to have, I still have n equals 0 to infinity. I'm going to pull this out and have it be negative 1 to the n. Okay, and then times x to the 2n. Let's make sure that works. This is 0 and then 1 squared. Yes, okay, that works. Okay, so I still have that alternating piece. That did not change, right? But now I need this to be 2n plus 1, right? Thinking about power rule, this is going to be x to the 2n plus 1 over that new power, and then times n factorial. And so that's going to be the series, the infinite series that is equal to that integral. And that's how we can use the series expansion to find integrals and do calculus on things that we might not have integration rules for.